there. All right, so today we're going to talk about logarithmic functions, and not a lot necessarily with our calculators so much today, but more just like recognizing the relationship between logarithms and exponentials. In the same way that addition and subtraction are inverse operations, or square rooting and squaring are inverse operations, exponentials and logs are also inverse operations. And so you can rearrange an exponential to look like a log and vice versa. So if you were to see an exponential, and this is what we have been working with here yesterday, was the exponential version. You can rearrange that into a logarithm. Now, let's look at how that gets switched. This was, remember, the base of the exponential. This is your exponent. This is the base. That base right there, whatever is being raised to a power, that is also the base of the logarithm. And actually, the log, and really by definition, if you look it up or Google it, it's the log is the exponent that you can raise that base to. So anytime you have a logarithm, it's always going to be equal to whatever the exponent was over here. So the log is the exponent that you can raise this base to get this value. So whatever exponent you got to raise this number to get to here, that's what the logarithm is. So yep, they both use the same base. Okay, just a few restrictions. B does have to be greater than 0. We're not going to deal with any negative. Well, really, let's look at this logarithm. That's what we're doing today. This is not going to be negative. It is not going to be 1. And this cannot be 0 because B to some power is never going to get you a 0 here. Okay, so here's what we've got. This is what we're familiar with. 2 to the 5th power would be a 32. This is what it would look like as a logarithm. It's a log. The base is 2, and I'm trying to get to a 32. So the log is the exponent that I have to raise this number to in order to get the 32. And so that exponent would have to be a 5. Now, just like yesterday, we weren't going to do a lot with graphs of exponentials. Same thing with logs, but it is important to have a kind of an idea of what's going on. Inverse graphs will always be symmetrical over the y equals x line. This line right here. So here is the exponential from yesterday. This is what a logarithmic graph looks like. Instead of crossing at 0, 1, it crosses at 1, 0. Inverses just swap their x's and y's. So yesterday we would have plotted at 2, 4. The logarithmic graph goes to 4, 2. All right, so just, again, recognizing those relationships. First thing we're going to do is kind of refresh your memory on just evaluating a log. This is a non-calculator thing here. You should be able to do some logarithms just off the top of your head. And so on all of these, we're just trying to figure out what is the exponent that I'd have to raise this base to get to this number. So we're going to start off with some easier ones, and then they're going to get harder, get some weird ones in there. So 2 to what power gets us 8? That should be a 3. All right. 2 to what power gets us 32? That should be a 5. 7 to what power would get you a 1? 0. Anything to the 0 power is 1. 4 to what power would get you a 2? Okay, now that's weird because I'm getting smaller, right? So what would be the power? Well, ultimately what I would want to do is I would want to square root the 4, and a square root is a power of 1/2. So 4 to the 1/2 is the same as square rooting it, which would get us to that 2. All right, so what about this one? 3 to what power would get us a 1/3? Okay, so now what I'm wanting to do is I'm wanting that 3 to drop to the denominator. So it's not going to change the value of it. So I want to say a 1, but what's going to make it shift to the denominator? Making it negative. Okay, so let's try another one like that. Here's 5 to some power would get us this 1 over 25. All right, so I'm shifting it down, so it's going to have to be negative, but this time I also have to square it. So this would be a negative 2. Next one, 5 to what power is the square root of 5? That's a 1/2. Last one, 9 to what power would get us a 1/3? We've got to shift it to the denominator. That's going to make it negative. But I also need to square root the 9, so it's going to be a negative 1/2. Now, I know you did this in college algebra, so hopefully those are making some sense to you. We're going to spend more time doing some of the more creative ones, and I say more fun. They're not quite as straightforward, but you can kind of think through them that same way. 3 to some power is going to get me this mess right here. This is not a calculator thing. We should be able to do this. So if I did not have the 4th root on it, and I just wanted 3 to some power was going to get me a 27. Well, I know 3 cubed is 27. So in my mind, now I'm kind of thinking through this here, I feel like I would have to take that 3 and I would have to raise it to the 3rd power. Now it's a 27. But I also have to 4th root it. Well, 4th rooting something would be a power of 1/4. So what I end up with here is 3 to the 3/4. Now, I'm kind of showing you the thought process on this, but remember the logarithm is just the exponent. So don't include this 3 as part of your answer. Your answer is just 3/4. Okay, let's try another one. Let's try this. I'm going to go to the right here. Let's try this. 9 to some power is a 27. Well, unfortunately, 9 to the first is 9 and 9 to the second is 81. And somewhere in between there's got to get me a 27. So here's the trick to this. I have to get this 9 and I've got to break it down. I've got to make it smaller. Couldn't I square root that 9? If I square root the 9, it's now in my head, it's a 3. And I can take 3 to a power to get 27. I would have to take it to the 3rd power, which means that I have 9 to the 3/2. And again, don't write that 9. It's just the exponent is your answer. So I'm going to get to the point where I don't really have to write this all out, because ultimately what's happening is anytime you're wanting to root something, notice that that number is going to be in the denominator. And then when I'm going to build it up, build it to a power bigger, that's going to be in your numerator. So a root is going to go to the denominator, a power is going to go up. So let's look at this one here. 16, I need to break it down. Now, my first thought is to square root it, because that's going to get me a 4. But 8 is not a perfect power of 4. So I've got to break it down more. I'm going to do the 4th root of 16. The 4th root of 16 would get me a 2. So since I'm doing a root, it's going to be the denominator. And the 4th root is 16, so that's a 2. Now I've got to build it back up. I've got to turn it into an 8, so I'm going to cube it. So it's going to be 3/4. All right, let's try this one. This is a little bit weird. 8, I'm going to have to break it down, so I'm probably going to be cube rooting it, right? 8 is a perfect cube root. Now, what's weird about this is that now I'm at a 2. But I'm trying to get this to happen. So I actually need to tweak this guy right here. I'm going to change that 4 to a 2 squared, and then take it to the 7th power. So really that's the equivalent of 2 to the 14th. So then back over here, if that's a 2 to the 14th, I have cube rooted the 8. Now I'm at a 2. So I'm going to build it up, and I need to take it to the 14th power. So my answer would be 14/3. Why don't you try some of these next ones on your own? Take a minute, work through them on your own, come back when you're finished. So go ahead and press pause. All right, so here are the answers. If you've gotten those answers correct, that's awesome. Why don't you just fast forward a minute here and move on. But I am going to go ahead and go through these because this is sort of new and it's more tricky than probably what you did in college algebra. So I want to make sure this makes sense. Now, ideally, you're able to just tell me the answer. But as I'm going through these, I'm going to go ahead and show you sort of the process. I'll show the work on it. So on this one here, this first one, I know that 2 is going to have to get built up to the 8. So I'm going to be cubing it. So that, because I'm cubing it, it's going to go in the numerator. So it's going to be a 2 cubed. Now that's an 8, but then I also have to fourth root it. So it's going to be to the 1/4. And right here is my exponent. Notice the 2 is not part of it. That's part of why I don't want you to do this, because so many people want to include that in their answer. Okay, next one. I've got this 8. First thing I want to do is I want to cube root that because that's going to cube root nicely. And that's going to be a 2 now. And what power do I need to take a 2 to get a 32? Well, that's to the 5th. Oh, look at that. I wrote that wrong. Oops. That's 5/3, not 5/2. Okay. Next one. I've got this 27. It's going to break down. So let's take it to the 1/3 power. That's a cube root of 27. So that's 3. And then I'm going to build that back up. 3 to the 4th power would get me an 81. So right there is where my 4/3 comes from. All right, last one. I was a little nicer on this one than the previous slide. 8 is going to have to get cube rooted. And then it's a 2. And I'm just going to raise it to the 5th. And there's my 5/3 right there. That's my answer. Okay, sorry about that goof up right there. Now, ultimately, what we're going to want to be able to do is to convert between exponentials and logs. And that's going to save us some time in solving. Yesterday, we did a lot of graphing. But we know, and you probably already know, there's a quicker way to do that algebraically, but you've got to be able to switch forms. And so today, this is a lot of mental math stuff today, and just really practicing getting this to make sense and be quick. To switch from a logarithm to an exponential, remember that it's this base value raised to some exponent will equal this value. We kind of think of it as the big loop here. So b to the y power is going to equal x. B to the y is equal to x. So then we're just going to practice that. We're not going to do any simplifying. We're not going to look for an answer. All we're doing is convert, convert, convert. And so all you're doing is this big loop. So x to the 2nd power equals 8. Do the loop. 4 to the 3rd power equals x. Do the loop. 2 to the x equals 10. And then I have a ton of, well, I say a ton, there's a few worksheets, but a ton of problems on that, just a boom, you just that muscle memory on your brain of doing that loop, do the loop, do the loop, so that you can quickly convert. And then in 3 weeks, when we've gotten out of this, you still have that muscle memory and you haven't forgotten it. Or maybe like when we get to the final, but we'll be using logs throughout the semester. So even just before that. Now, can you go the other way? Can you take an exponential and switch it to a logarithm? Okay, so remember that the base is the same. So this is going to be a log. The base is 8, so it's going to be log base 8 of 2, that is called the argument, equals your exponent. That's what I always say in my head, equals the exponent, always equals the exponent, equals the exponent, equals the exponent. All right, so log, the base is x, of 20, again, that's called your argument, equals your exponent. The log, base 5 of x equals your exponent. There we go. I mean, seriously, like that's what we're doing today on our homework, is just boom, 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 getting really good at that. Now, we do have a couple special logarithms out there. One of them is called common log, and it's the one that is used commonly because it is a base 10, and it converts nicely using scientific notation, times 10 to a power. And so that's why logarithm with a base 10 is called our common log. It's so common that we shortcut it and we don't even write the base 10. This is the log button that's on your calculator. It is a common log assumed to be a base 10. So let's do some evaluating with common log. So assuming this is a 10, remember you're just evaluating 10 to what power would get us a 100? Well, 10 squared would be 100. So your answer is 2. Okay. 10 to what power is 1 over 10,000? Well, it's going to the denominator, so I know that's going to be a negative exponent, and that's going to be a negative 3. 10 cubed is 1,000. All right. If we were trying to do some converting with common logs, again, assuming there's a little 10 right here, then you switch this to an exponent. 10 to the x is equal to 7. All right, we have one more. We talked about the natural base yesterday of E, and so that also is a common one. It occurs a lot in nature and in a lot of our formulas. So a log base E of x is actually shortcutted. We call it natural log. It's switched around ln. I don't know why. I'm sure it's Latin or something, but we write ln. You can write ln with capitals. Some people do cursive. Some people write it, I mean, I don't know, you could do this, ln. Some people do this, but be careful. We don't want it to look like one N. So just as long as you can keep it neat and you can tell what it is. All right, so instead of writing log base E, we write this ln. So this right here, in our mind, we're thinking there's a little e right here. We don't write it, but we think it is. So e to what power is e to the 4th power? Okay, some people that seems confusing. E to what power is e to the 4th power? Oh, it'd be a 4. It's got to be a 4. Okay, how about this next one? Assuming there's a little e here, but we don't write it, it's got to bump to the denominator, but it's still to the 1st power. So that's going to just equal negative 1. All right, if you want to convert between a natural log and an exponential, again, assuming there's a little e right here, then you would do your big loop. So there's an e to the 6th equals x. And that's what it would look like as an exponential. Okay, just a lot of practice of that stuff today. Homework is probably a bunch of worksheets. All right, good luck.